Guys, what's the crack? Hi, Omar. Straight on it. How are we doing? Last day of summer school. Omar, did you do any other summer schools? Any other any other subjects? Hi, JMB. Hi, Ishak. Hey, guys. How are we doing? Last day of summer school. We're doing astrophysics today. Hi, Nalia. Did you guys do any other summer schools, or did you stick with physics? I don't even hear my dog, but he's going mad right now. Math and chem. Oh wow, JMBs, you don't have quite a few of them. How you find them? Obviously not as good as physics though, right? So today they're pretty chill. That's good. You don't want to be stressed, right? So today what we're going to do is astrophysics, like I said. So this is. Oh, can you hear him? Yeah, he doesn't like. So obviously he's not around the room when I'm doing my streaming because he's a bit mad. But he also thinks right now that I'm obviously got someone in the house that he hasn't seen. I'm chatting to him, so he's going crazy because he hasn't got to sniff that person out. Little does he know, I'm literally probably sitting in a room talking. Well, I'm not obviously not talking to myself, but this, to him I am obviously. Okay, so yeah, astrophysics. I love this topic. This one is an optional topic. So it depends. Do you guys know what your optional topic is? So different teachers will have different optional topics. So I've always picked astrophysics because I loved astrophysics because I did it at uni. But at the same time, I know I was talking to some people, medical physics. I know I was talking to some people that were saying they wanted to do astrophysics university, but their school isn't choosing astrophysics as an optional topic. And if that's the case, write in on your CV or talking about in your interviews saying that you did it in summer school or saying that you did it for the year with me is a good way to talk about in your interview how you've shown that you're like trying to push yourself beyond what you already know, like how much you're excited or interested into the topic. Medical physics. So medical physics is really similar to astrophysics at the start because you have to do quite a lot on lenses. So like the lens formula, the lens equation, which is again a big topic at the start of astrophysics. Now that you think astro, but you would have wanted astro or electronics. Yeah, I think astro is mad interesting. But medical physics is obviously a massive part of physics, right? Like especially now about biomedical arms and looking at pacemakers and all of that. So most of that is physics, not actually biology. Is it possible for some teachers to split the class into two? Yeah, it is possible, but it's quite rare because a lot of high schools don't have multiple teachers that can teach physics, right? So, for example, in my school, the school I just left, we only had myself teaching physics, right? And we had a trainee teacher who, so like what that means is like a teacher who's just started teaching, so they're not able to take a full year 13 course himself. But if you're lucky enough that you've got like two teachers at school who can both teach physics at year 13, then yeah, you can ask them to do that. Omar, Ash is the best. I agree. I agree. It's just cool, right? Because it's like it's so out there and it's actually really new, so it's very different. A movie I just started watching the other day. Do you guys have you guys watched Take Me to the Moon yet? Take Me to the Moon. Was it you guys I was talking about? We were talking about how it's got Shannon Tatum in it. So it's like a movie about how they go to it's about how NASA and the Apollo 11 mission and the space race, they're trying to get to the moon first, and then she's like trying to like film it or trying to like get people more interested in it because you think about the wars that were happening then, people didn't want to be spending all this money anymore in the Apollo missions because so many of them been unsuccessful. It's actually really good. Well, I've only watched the intro to it, but I'm gonna finish it off tonight hopefully. um But yeah, I just think it's really interesting that I think to see how like the backstory behind NASA and like what it was really like day to day for the scientists, because obviously you have the Cold War, but I mean also America was funding another war that was happening as well. And a lot of people in America weren't happy about it and didn't want their soldiers to be sent over. So the Cold War wasn't actually any fighting, like obviously you know that. Um I want to say it was one in Vietnam, but now I'm forgetting. Pretty sure it's the one in Vietnam. I don't remember. I'm gonna Google it now in a second. Or actually, maybe you guys might know a bit history better than me. Um, but yes, that's what we're gonna do today. Nam, thank you. Yes, 100% true, GMB. Yeah, which is why a lot of people in America weren't happy about it, and then find out they were spending money on NASA. And they also weren't happy about, so that it was trying to like the movie shows you a little bit of the background, like what was kind of going on around that time as well, and why it was so difficult to get funding for NASA. So yeah, I just find all this stuff mad interesting. So what we're going to look at today is looking at basically about like what redshift is, how do we calculate how old the universe is. So just stuff that is quite interesting part of astrophysics. So it says, using the images, where do you think we put telescopes that observe the UV region of the EM spectrum and why? And just a little reminder that UV means ultraviolet and EM means the electromagnetic spectrum. So have a look at the picture. So hopefully you're looking at UV. Where do we put telescopes that observe UV region of the EM spectrum and why? In space, the Earth atmosphere absorbs most of the UV region. Yeah, beautiful, good job. Yeah, so what we're going to do is we're going to put most of the telescopes in space, right? Because ultraviolet light, we know, so that graph maybe is not the best one to show you about the UV, it's better for the IR, but we know that a lot of the UV doesn't reach the Earth, right? We know that because UV, you learned in GCSEs, that one can cause skin cancer. So the fact that all of us aren't dying of skin cancer every day shows us that a lot of the UV doesn't reach the surface of the Earth, right? So because a lot of the UV doesn't reach the surface of the Earth, and you kind of see that the graph there is tending to go down towards zero in the UV region, because a lot of it doesn't reach the Earth, we have to put those telescopes into space, right? So any observations we want to do in the UV region, we have to launch the telescope on a rocket out of space, and then that's where we put the telescope. Okay, so it says some IR, so IR, remember, is infrared. Some IR can reach the surface of the Earth, right? So it says percentage of energy arriving at sea level. So if we look at IR, there is some regions of it where nearly 100% is reaching it, but some regions where barely any. Okay. But it says molecular absorption in the atmosphere. Water absorbs a lot of the infrared region of the spectrum. So where do you think we have to put IR telescopes if they can be placed on Earth? So again, we know IR can reach the Earth because we're hot, right? We can feel the heat from the sun, infrared radiation. But where would we put them on the surface of the Earth if we're trying to observe the IR region? Knowing that, looking here, water absorbs a lot of it. So where would we put them? Yeah, like deserts. Yeah, really dry locations. Good job. So we're going to put them in really dry locations. And we're also going to put them really high up, right? We're probably going to put them in mountains because you think about it, we know the surface of the Earth, there's loads of atmosphere. The atmosphere is really thick at the bottom, right? That makes sense because we're all breathing loads of oxygen. And then as you go further up away from the surface of Earth, the atmosphere just starts to get, so it's really, really dense here, and the atmosphere then just starts to get kind of thin. So then if water is absorbing a lot of those IR rays, there'll be less water, less dense water higher up. So if I put my telescope on the surface of a mountain, then I've got less worries about detecting those wavelengths. Okay, next one. Why do we put visible telescopes and radio telescopes in remote areas? So again, down here, we can say atmospheric opacity. So again, we can see that gamma rays, X-rays, UV light is 100% opacity. They can't get on the surface of the Earth. And if we look at our IR region, so the infrared region, we can see that some of them can reach the surface of the Earth. But visible light, we know can reach the surface of the Earth, right? Because we can see everything. And we know that radio, look, basically all of radio can reach the surface of the Earth. And here's a picture of a radio telescope. So why do we put them in remote areas? Yeah, good job. Because mobile phones, so mobiles give off radio waves. We know about radio stations or radio communications. Okay, so if I'm observing space, I don't want any of the communications from people just being around affecting my results. So maybe I'll get a spike. Maybe I'm looking at data and I'll get a spike in results. And I think, oh my goodness, I found something in space, right? But then I find out just a person walked past and they're using their phone or they're using a radio. Okay, so we want to make sure we put them in really remote areas. So remote basically means like they're deserted. There's no people there, or less people anyway. So no people there. And if about visible telescopes, what's the process? Yeah, interference. Yeah, good job. I just saw it there. IRAM, lovely. Because of light pollution, right? Because of light pollution. So then again, you know that, right? So most of us live in London. Most of us live in London. At nighttime, I can barely see any stars because there's loads of light pollution in London. But if I was to go home to Northern Ireland, where I'm from, and I look at the sky, I can, even though I do live in a big town, I still would see a lot more stars in the sky because there's less light pollution. So hi Kai, hi Static Spark, and hello yet. Yeah, beautiful. Good job. Okay, so moving on. So the next thing I'm going to talk about is how do we actually look at stars in the sky. So it's called the magnitude scale. So around 120 BC, there was a Greek astronomer, Hipparchus. So it's called the Hipparchus scale. He basically, obviously he wasn't the first man to look into space, look into the sky and try to name the stars. But because of the way history books are, it was the first catalogued one, right? So it's the Hipparchus scale. So when he looked up at the sky, he decided he's going to use a 6-point scale. So he decided we're going to put 1 being the brightest object in the sky, and 6 is going to be the dimmest object in the sky. Okay, so if he saw a really bright star, he's going to label it 1. Really dim star, he labeled it 6. Okay, and then what he said, between the numbers 1 and 6, there's 100 times difference in brightness. So a magnitude 1 star is 100 times brighter than a magnitude 6 star. Okay, so just to see if we're good, how much brighter do you think a magnitude 3 star is than a magnitude 1 star? So 2, 3, 4, 5. How much brighter do you think a magnitude 3 star is versus a magnitude 1 star? How do we do it? Yeah, so judged by eye. So it's way back in time, like 120 BC, before Christ, right? Ages ago. When they just looked at the sky, they categorized the stars, what they could see, right? Because think about like their eyesight, telescopes, everything that wasn't as good. So anything that was really bright, they said, we're going to give that number 1. Anything really dim, we're going to give that number 60. Oh, so 50 is a good guess, but no. So if you look at it here, do you see there's 1, 2, 3, 4, 5 jumps between the number 1 and 6? So if a magnitude 6 star is 100 times brighter, what we do is we do 100 and we take the 5th root of 100, and the 5th root of 100 is 2.5. So a magnitude 2 star is 2.5 times brighter than magnitude 1 star. A magnitude 3 star is 2.5 times brighter than magnitude 2 star. So what we have there, so magnitude 3 star is going to be 2.5, and it's going to be 1, 2 jumps. The difference is 2, so 2.5 squared. So if you do 2.5 and you square it, you get a number of 6.25. So 6.25. So a magnitude 3 star is roughly 6 times brighter than a magnitude 2 star. Yeah. So that's how we do it. So again, 1 to 6, we have to learn that off, that it's 100 times brighter. And then we can see there's 5 jumps there. So take the 5th root of 100 to get 2.5. And then so every number is 2.5 times brighter than the previous number. So that's the scale they did. Okay. How come some stars then do look brighter than the others in the sky? What's the reasons why? So how come some stars in the sky look brighter than others? What would be the reasons why? Yeah. Ayo, beautiful. JMB, good. Yeah, brilliant, right? So here's surface of the Earth. There might be a star right here, and there might be a star way over here. Clearly, this star, we know that, yeah, JMB, literally I was about to that. Good job. Because the inverse square law, we know the light from that star is going to have much higher intensity. So this one probably looks much brighter because of the inverse square law. Remember, the inverse square law is intensity is inversely proportional to the square of their separation. So we can say that the brightness is inversely proportional to the square of their separation. Where this star, the light has traveled so much further, so R is much, much bigger, so the intensity is much, much lower, or the brightness is much, much lower. So yeah, it could be because one is just brighter than the other, and it could be because one is closer than the other due to the distance. And then, like Io said there, it also could be due to their size, right? So if this star is much smaller and this star is much bigger, clearly this star is going to give us much more light than the other star. So the 2 reasons why stars look brighter is because either their size or because their distance. So we had to make laws about that. We're going to learn about those laws. So like here's an example here. So Big Dipper, most people know about the Big Dipper. So there's a Big Dipper. And the Big Dipper, what they did was they had 7 bright stars. So 6 of them are second magnitude. So that means we can obviously see them from Earth because it's magnitude's 2 star. So we can see from Earth 1 to 6, magnitude 2 star. And one of them is a magnitude 3 star. So that's why we can see those stars on the surface of the Earth. So if we can see them from the surface of the Earth, we know they're always the numbers 1 to 6, right? So we can see them from the surface of the Earth. Okay, so what they did then, because we know there's we got telescopes that are much better, right? We can see further away back in time. We can see much more brighter stars. We can see different galaxies now. We can just see a lot more in the universe. So what we realized is 1 to 6 wasn't good enough scale. There's some stars that we observe that are much, much, much brighter than 1. So if they're much, much brighter than 1, that means they had to be in the number 0, the number is -1, the number is -2. So clearly you can see the more negative the star is, it's actually more brighter. And if we see a magnitude 10 star, something really, really dim, we couldn't see with our eyes before, but now our telescopes are so good, we can see it. It's going to be a really high number. Okay, so because of this scale, 1 to 6, with 1 being the brighter, now that we can know that there's much brighter things in the universe, like supernovas we can see, and we can see quasars, there's so much brighter things we can see. Now we have a thing called the magnitude scale. So the magnitude scale, how we do it is, m, the little m, is called your apparent magnitude. Okay, so apparent magnitude is what we can see from Earth. So their apparent magnitude. So what it looks like if I'm on the surface of Earth looking at the star. Capital N is the absolute magnitude. So that means it's how bright the star actually is. Okay, so we take into account where it actually is in the solar system. And the way to relate those two numbers is we do 5 log to the base 10. So anytime we write log, so log is always the base 10. And hopefully you know from math, capital L, small ln is always the base E. Right? So logs is always 10, lins is always to E. So because it's log, it's the base 10 of the distance measured in parsecs. Okay? So what a parsec is, it was a unit we defined. Parsecs do arcsec. So we know we're on Earth, right? So here's our Earth. And we know that we orbit the sun. There's the sun. So let's say we're looking at a star way over here. When we look at the star way over here, that's what the star looks like. And we've got all our background stars as a reference. And then 6 months later, we're over here in the Earth. And again, there's where our stars looks like. And there's all my reference stars in the back. So how we'd actually define this distance. So we've always said from the distance between the sun and the Earth, we now call it 1 astronomical unit, 1 AU. Okay? Because we know the distance sun and Earth. That's our reference point, our rotation around the sun. And then 1 parsec is this distance. The distance to the star when this angle is always going to be 1 arc second. Okay, so that's why you define a parsec. Oh, you've heard of them? Yeah, so 1 parsec is when we have an angle of 1 AU and the angle there of a sustension of 1 arc second. Okay, so that's how we define things in space now. 1 arsec is just like, we know we do trig. So like if you have your hypotenuse and your base, if the base is 1 astronomical unit, and the height is 1 parsec, that's what we call that little angle in there now. We call it an arc second. So sometimes when you look at the sky, you'll see that people define them by arc seconds, like 5 arc seconds, 1 arc second, or 5 parsecs away. It's our reference to how far away things are. So a lot of you have already heard of light years. LY is light years. So light years is a way to tell how distant things are away. Meters is another way to say how far things are away. And parsecs is another way to say how far things are away. And we use a parsec because we use that reference base there of the Earth orbiting the sun to see how these stars change where they're at. Okay, so we're just going to practice doing some of this math. Okay, before we practice it, there's just one more thing I want to talk about. So we just said that we know stars are brighter because either they're closer to us or because they're bigger, right? So there are 2 laws were to do with that. So we got Wien's law and we had Stephan's law. Okay, so Stephan's law was, some people there talked about brightness, right? So Stephan's law, it says that the power, so the power output of the star is due to sigma times by its area times by the temperature to the power 4. Okay, so what we're saying is we have to take into account the area of the star. So stars with a larger area will also be brighter, and stars with a bigger temperature will also be brighter, right? And then the other law they looked at was they saw that when we look at stars, so we know when we have a star and we're on the surface of the Earth and all that light reaches us, we can look at that light. And when we look at the light, P, Q, and R, we can look at the light and how that's distributed over the wavelengths. And we can look at that light, and the light will tell us what temperature that star is. Because of Wayne's law told us whatever the peak wavelength is at, so here's my peak wavelength, if I multiply by whatever temperature is, we always get the same constant. So to find the temperature of those stars, we just find what the peak wavelength is and divide by this number to find what the temperature of the stars is. And then that's how they classified all the stars. So they started classifying the stars by their temperature. So you've probably heard people say like an O-class star, a B-class star, an A-class star. And the way to remember it is O, B, A, fine girl, kiss me. Such your order of stars. So an O-class star, a B-class star, an A-class star, F star, G star, K star, and an M star. Denise know in the chat, what spectral class is our own star? The sun. Pop in the chat. Does anyone know what spectral class our own star is? The sun. So maybe you look at that table to figure out what it is. What spectral class, O be a fine girl, kiss me, is our own sun? So we're saying Ao says F, Kai says G, Iram says G, Carl says M. Yeah, most of you, yeah, Nalia and Iram there, perfect. So we're a G-class star. Yeah, JB, Omar, G-class star. So our sun is a G-class star. Roughly, it's around 6,000 degrees Celsius. So our sun's roughly around 6,000 degrees Celsius. And that's why the color makes sense, right? Our sun is kind of yellow. So we know things, if you know in chemistry, when you did it in GCSEs, you've got the Bunsen burner flames. And you've got the orange flame, which we said was like the smoky flame. And then you had the blue flame in the middle. Remember, we said it was like the clean flame or the hotter flame. So blue is always our hotter colors. So OB is really blue colors. And then colder colors is when you're going towards your orange and your reds. Yeah. So depending on what, yeah, we're going to look at the JMB. We're going to look at the cycle of stars in a second. But yeah, so the cycle of stars, what its temperature, its spectral class will depend on where it's at in its lifetime. So if it's a main sequence star, or if it's a red giant, or if it's a white dwarf. Okay. Another thing that's quite interesting is what we can look at hydrogen Balmer lines. So what we can do, does anyone do chemistry? And in chemistry, we see energy level diagrams. Hydrogen Balmer line means that all of our electrons are in the n equals 2 state. And in chemistry, you've probably learned, that all the electrons are normally in the ground state. So n equals 1 is our ground state. But if the electrons aren't in the ground state and they're in the n equals 2 state, that means they'll be excited. And the only reason that all of our electrons will be excited is because it's really hot. So that's another thing we can do. We can look at the electrons and see where they are, or we can see if they get where they start and where they end to see what temperature that star is. So hydrogen Balmer lines, that's what we've written here. So our H lines are hydrogen Balmer lines. They're really strong in our A-class stars. So you can see there's quite a few ways that we can figure out how hot or what age or what temperature stars are. We can use Wayne's law down here. Sorry, I can't spell Wayne's. We can use Wayne's law down here to look at the just distribution of the wavelengths. And wherever the peak is, we divide by this number to get its temperature. Or we can see, is there any hydrogen Balmer lines? And if there is hydrogen Balmer lines, I know it's going to be an A-class star, so like a super hot star. Okay, really quickly in the chat, does anyone remember what Stefan's law was? What was Stefan's law? So what did he relate? Stefan's law related 3 things really. Pop in the chat. What was Stefan's law? Then we're going to do this Wayne's law. Then I want to ask what absolute magnitude is, and then what Hipparchus scale is. Yeah, good job, Iram. Lovely. He said the power of a star is directly proportional to its surface area. So we know surface area, if we model them as spheres, that's going to be 4 pi r squared. 4 and a volume 4/3 pi r cubed. Yeah, 4 pi r squared, that's our surface area. And he said the power is also directly proportional to the temperature of that star, the power of 4. So that's why I look at the brightness. Yeah, power, thank you, Priscilla. Yeah, and hello, Priscilla. Area, power, and temperature. Wayne's law, what did he say? So he said something about this graph. How could we look at the wavelengths given off by a star? What was that tell us? So this axis is my wavelength. And that's how I remember it. W and W. So he did something with the wavelengths of star. So Wayne's law said something about wavelengths. So how do we use the graph of the wavelengths of the light from a star? What can we figure out about the star based on its wavelength? Yeah, good job. So what we did was we find where that peak is. So we find what that peak wavelength is. Yeah, good job. So whatever that wavelength is, the peak wavelength times by the temperature equals some constant. So what he really saw was there, the peak wavelength is inversely proportional to its temperature. So you see the wavelength in the peak would be equal to some constant over its temperature. So that's how he got this last bit. So he saw the wavelength that we see is inversely proportional to the temperature. So that's what he figured out. So that's now when we look at the stars, when we look at the spectra of stars, when we look at the wavelength of stars, we can now figure out what temperature they are based on Wayne's law. Yeah, nice. Okay, what is absolute magnitude? That one was the capital M. What's absolute magnitude? Or what was the other word? How's it different than the other word? So the equation, if we look at m minus m equals 5 log the base 10 of d over 10 in parsecs. So we said this one was our apparent magnitude, and that's how bright it seems from the surface of the Earth. And m, yeah, m is your absolute magnitude, and that's just how bright it is for where it is right now. Right, so it's how bright the star is itself, it's not taking into account anything to do with distance. Or we could say how bright it is if we take it at a distance of 10 parsecs. Okay, so again, apparent magnitude is going on again. Apparent magnitude is we're on the surface of the Earth, and I've got all of those stars all over the place. Apparent magnitude just says how bright they are from the surface of the Earth. Okay, whereas absolute magnitude is more useful because what it does is it looks at how bright they're on the surface of the Earth, and it says, what if we put them all 10 parsecs away from Earth? So if we put them all 10 parsecs away from Earth, how bright would they be then? So it's getting rid of the distance. We're just looking at the size then. So again, if we move this star to 10 parsecs away, how bright would it be? If we move this star to 10 parsecs away, how bright it would be? If we move this star to 10 parsecs away, how bright it would be? So absolute magnitude is more useful because it's telling us basically what the apparent magnitude would be if all of the stars were placed at 10 parsecs away. So it's kind of getting rid of that distance factor. So that we can see if a star is brighter, it must be because it's a much bigger star. Okay, and then last one then, what was the Hipparchus scale? What numbers did it range from, and what was the difference between the numbers? So what's the Hipparchus scale? What numbers did it range from, and what's the difference between the numbers? Okay. So remember he said Hipparchus scale was some guy, he was on the surface of the Earth, he looked at all the stars in the sky, and he classified them. Yeah, Iram, thank you. He classified them from 1 to 6. Nice. Yeah, nice, good job. With magnitude 1 stars being 100 times brighter than the magnitude 6 stars. Yeah, JMB, lovely. Yeah. Rameshmir, I haven't seen you yet. Hello. Ashna, hello. Yeah, 1 to 6 scale. Good job. And then what we can see then is between the stars, there's been a factor of 2.5 difference in brightness because we take the fifth root of 100 because there's 5 gaps between them. Nice. So the Parker scale is classify stars from 1 to 6. 1's the brightest, 6 the dimmest, and the difference in factors between them was 100. Easy. Okay, next one is stars' life cycles. So a lot of people know quite a bit about this anyway if I researched it before. But hopefully we know that nebulas is when we have our clouds of gas and dust, right? They're already cold. That's the beginning, basically, of formation of a star. And then after the nebula, what's going to happen is we know gravity likes to pull things together. So gravity wants to pull everything together, and that's why the temperature starts to rise. And when the temperature starts to rise, we then form a protostar. So a protostar is like the beginning of a star. Then a main sequence star is currently what our sun is. So our sun is called a main sequence star. If our sun, less than 3 solar masses. So we define everything by the mass of the sun. So our sun is clearly less than 3 solar masses because our sun is 1 solar mass. So our sun, what it will do is at the end of its life, it will approach a red giant. So it'll start to swell. It'll start to swell from a red giant. Red means it's obviously cooler, right? Because right now we're kind of yellow. Remember, red is cooler. It forms a red giant. And then after it forms a red giant, all those outer layers will get pushed out into space and will get left behind with a white dwarf. And when the white dwarf keeps cooling down, that's how we get left with a black dwarf. You can't see a black dwarf anymore. Okay. But if anything is heavier than our sun, so greater than free solar masses of our sun, 3 times the mass of the sun, they will all do supernovas. So we're lucky, our sun will never supernova, because if it did, well, if our sun was dying, we'd all be dead anyway. But if our sun did supernova, it would completely wipe us out, like an instant. So our sun will never supernova because it's so small. But anything 3 times bigger than our sun will do supernovas. They'll form red supergiants, and then they will supernova. And then depending on their size, they will either leave us behind a neutron star or they will leave us behind a black hole. Okay, so black holes are like a big part of research right now. You've probably heard about them quite a lot. So black holes are always formed by supernovas by really large stars. Okay, so what we just said is we're going to learn about 2 different types of supernovas. So loads of people know about a supernova from exploding stars. Okay, so they're called type 2 supernovas. Okay, so there's different types of supernovas. A type 2 supernova is when a star explodes. A type 1 supernova we're going to do about in a second. So type 2 supernovas is anything greater than the mass of the sun. And if it's much bigger than the mass of the sun, that's when we're going to get a black hole given out. And a thing called a gamma ray burst, or you might see it written sometimes GRB. It's called a gamma ray burst. It just means really high energy in the gamma region. So what is about a black hole? So a black hole, this is me trying to show you one here. Black holes we can't see, right? They're black. But do you see how if the black hole's in the middle here, because gravity pulls things in, if there was a star here, if the star gets close to the black hole, that star will start to get sucked in to the black hole. So as it gets sucked into the black hole, we can see the light from that star starts to spiral. So that's how we figure out what black holes are, because everything around them is getting sucked in. So the light spirals around it until it gets sucked into the black hole. So there's a point around a black hole called an event horizon. So for this black hole would be the event horizon. And the event horizon is the point at which if you go beyond the event horizon, anything will get sucked into the black hole. Okay. If there's supermassive black holes, you're also going to have quasars around them. So what that means is you're going to have like beams of radiation given off, jets of radiation given off as matter falls in black hole. So as this matter falls into black hole, a supermassive black hole, we're going to get active galactic nuclei. So they're active. That's why we're giving out quasars. So we talked there a minute ago about the event horizon. So we can calculate what that event horizon is by doing 2 times G. So G, we know from our gravitational fields topic, remember 6.67 times 10 to the negative 11. M is the mass of it, and C is our speed of light. So 3 times 10 to the power of 8 meters per second. Okay, we're going to quiz you and then ask me questions. Okay, so this was a past paper question here. What is meant by a supernova? Pop in the chat. So I had it written on that last slide. What is a supernova? What is a supernova? So like a 1-mark question. Yeah, it's going to be an explosion. Explosion when the star dies. Yeah. How would we know an supernova happened? That's kind of what I'm asking more. So like if I'm observing the sky, what would change for me to know there's been a supernova? Star explodes. Yeah. So what would I observe to know there's been a supernova? So I'm looking for a telescope. That's what the definition is. It's to do with what you observe. Yes, IREM. Beautiful. That's the perfect definition, right? The definition for AQA is a rapid increase in brightness. So supernova is when the star explodes, you're right. But what we observe is a rapid, like a really fast increase in the brightness. Okay, so that's when a supernova happens. So as you're looking at the star and you see this explosion of light, because that's how we know a supernova has then happened. So it's a rapid increase in brightness. Okay, what is a neutron star then? So what is a neutron star? What is a neutron star? What is a neutron star? Yeah, Omar, yeah, you get marks for very dense. That's true. It's a 2-mark question. They're very dense. Yeah, actually, JMB, they want that in your answers in AQA. If you say it's very dense and it's made of neutrons, you've basically got your 2 marks. Yeah, good job. Instead of saying dying star, what would you say? It's formed after a what? Yeah, thank you, Ikir. Formed after a supernova. Yeah, nice, good job. So a neutron star is extremely dense. It's made of neutrons and it's formed after a supernova. Yeah, and it's formed less than 3 solar masses, Carl. Yeah, good job. So anything less than 3 solar masses. Okay. So it says here, if we're looking at this star, it's a red supergiant in constellation of Scorpio. It's got 18 times the mass of the sun. It's probably not going to form a neutron star. That's actually going to end up forming a black hole. Okay, so it says to become a black hole, it's likely the core would have to have a mass at least twice that of the sun. Can you calculate the Schwarzschild radius? So the Schwarzschild radius is kind of like the event horizon of a black hole with a mass twice that of the sun. So remember, G is 6.67 times 10 to the negative 11. And if you have your data sheet, you can see that the mass of the sun, I have my data sheet here for you in case you don't, the mass of the sun is 1.99 times 10 to the power 30 kilograms. So can you figure out what that Schwarzschild radius is, or what the event horizon is for a black hole, for a star basically, that's got twice the mass of the sun? So it's going to have 2 times the mass of the sun. So that's how we're going to represent the mass of the sun. Mass of the sun. What is that Schwarzschild radius? Yeah, Ikir. Yeah, awesome. Yeah, Garrick, awesome. Thank you for answering. So what is that radius? Just see me pop the math in your calculator. So Schwarzschild radius tells the event horizon, the point from which, if you go beyond the event horizon, the escape velocity of an event horizon is beyond the speed of light. So nothing can escape it. The way to find out the size of it is 2 times g times the mass of the speed light squared. So RS, our event horizon, or Schwarzschild radius, is 2 times g. I didn't get that number right here. Did you definitely do 2 times the mass of the sun? Times by 2 times by 1.99 times 10 to the power 30. Divide it by, and did you square speed of light? 3 times 10 to the power of 8 squared. Iram, I got same as you. Yeah, good job. So I got same as Iram, 5.9 times 10 to the power of 3 meters, or 5.9 kilometers. Yeah, lovely. Ashna, did you multiply by 2? Because remember, there's a 2 there already. And then we were told the mass to use was 2 times the mass of the sun. So it's actually a 4. We're multiplying by 4. So just be careful there with that one. Yep, Priscilla, Nalia, same as you guys. Iram, same as you guys. Yeah, Omar and Ashna, is it the 2 you missed? The second 2? Because it did say 2 times the mass of the sun. So when you had the mass of the sun, you had to multiply the number by 2. But there already was a 2 in the equation. Right, because there already is a 2 in that equation. Yeah, grand. Yeah, Carl, perfect. Omar, perfect now. Grand. Yes, all good. So again, that's how we figure out the event horizon, or the Schwarzschild radius, of our black holes. Okay, just to make sure we're good, because these questions come up quite a lot in the paper. What is a supernova? What did we say it was? A lot of you got it there at the end. Yeah, Akir. Yep, you're on now. So what is a supernova? You want to begin with the word R? Word beginning with R. Something. So yeah, this one comes up quite a lot if you do AQA, paper 3, section B. Yep, a rapid, good job, a rapid increase. Yeah, AO, so that's technically what a supernova is, but we define it by what you'd observe. So we observe a rapid increase in brightness. So that's what we observe, a rapid increase in brightness. Yeah, Ikir, lovely. Yeah, rapid brightness. Yeah, rapid increase in brightness. Omar, perfect, good job. Okay, what did we say the event horizon was? So around a black hole, there is an event horizon. What do we say the event horizon was? Or the Schwarzschild radius? So what's the event horizon? So first mark is because we said event horizon is around a black hole. We're telling the examiners we know that's where it is, but what is it? At here, yeah. So I was saying that medical and astro are really similar for the first few lessons because most of it's about lenses. But like I said, like a lot of people, they want to study astrophysics at uni. And when you go to your interviews, so if you do interviews for university or you write in your personal statement and you apply to something like astrophysics, a good thing that you could write about now is that you said you did summer school and you did astrophysics lesson on summer school with My Ed Space, or you could say that through the year when you did summer school with us, you did, even though you learned medical physics in school, you did astrophysics in an extra topic. So I think it'd be quite nice as well that to talk about in interviews, just to be like show them how you went above and beyond the learning you did in school, because it's what they like to hear about, isn't it? How you're different from the other people. Yeah, Iram, nice. Yeah, Iram, nice. We want to talk about the speed of light, nice. So it says black hole is the region around a black hole where the escape velocity, so the escape velocity means the speed you need to leave, escape velocity is greater than the speed of light. So what that means is even light is not traveling fast enough to escape. So if light passes beyond this event horizon, it'll get sucked into the black hole because the escape velocity is greater than the speed of light. Interviews are only done by a handful of unis, yes. JMB, yes, they are. However, the ones that interview are normally the ones that are more selective and the ones you want to go to. And the ones that don't interview, you need to make sure that your personal statement has got something written on it that makes sure you show them that you didn't just get A's in school, right? Because you think about it, and that's like kind of a bit of advice there for your personal statements. If you're applying to somewhere like BAF, so for example, BAF doesn't do interviews for natural science, right? So let's say I'm applying to BAF, their entry requirements is AAA, right? Normally, or it's going to A star A B, right? So they've got really high entry requirements. Everyone applying to that uni, they're not going to let in anyway if they don't have A's. So you just trying to say that you study loads in school and you work hard in school isn't what they're looking for, because they're getting that anyway by you getting A's. You need to have something in your personal statement that shows that you are different from the other people that are applying that also are going to get A's. So that's why this is something nice that you should definitely write about, is like how you did summer school, how you learned about extra topics. Maybe you could write about that you're doing medical physics as an optional topic in AQA, but you really liked astrophysics, so you learned it yourself at summer school, or that you did it for the September course with me. So yeah, just like when you're thinking about your personal statements, you need to have something there that makes you different, makes you stand out, even if you don't have the interview. Hey, here, you want to do Astro at uni? That's what I did. Oh, you probably know that's what I did. I've said it a few times today, haven't I? But yeah, if you want to do a uni and you're going to write a personal statement to apply for an astrophysics course, that's a good thing to write about, to be like, oh, even though my teacher is teaching me medical physics, I'm going to do the summer school where I did astro, or I'm going to do the September course where I did astro. Yeah, Kai, 100% put summer school in there. Yeah. So I would probably write about how it's called. Yeah, so don't just write I went to summer school and learned astrophysics, or I went to summer school and did physics. Make it sound obviously a little bit better, right? So it'd be like, um, over my free time this summer, I decided that I wanted to expand my knowledge and research further into different topics in science that I didn't do about in school. For example, one of those things was astrophysics. So I attended I attended a 4-week course with My Ed Space where I learnt about XYZ. Priscilla, a certificate of completion. That's a really good idea. But because this course is free and open, it's really hard to tell. So like you guys have also been really active in the chat, but like sometimes I get it, like you don't want to type the whole time. It's really hard to tell. But if you're writing an interview, you don't really need a certificate of completion. You would just tell them that you attended the 8-week course. Yeah. Okay, so sorry. What's the difference between a neutron star and a black hole? So what's the difference between a neutron star and a black hole? Especially actually just thinking there now you're saying it. A lot of you did some of you were there saying at the start, was it Omar saying at the start that he did the chemistry and math one as well? Like 100% right about that stuff in your personal statement. Don't be writing a full paragraph on it. Like you don't want to bore them, but definitely a good 3 sentences, maybe 2 sentences. Or if you don't have any other extracurriculars, it's definitely a good thing to pop in. Okay, so what's the difference between a neutron star and a black hole? Yeah, a black hole is formed after a supernova. Good job. So actually both of them are. So something that's similar is that both are formed after a supernova. Neutron stars form from stars with mass of less than, yeah, good job. Neutron stars are formed after a supernova. Neutron stars are formed from stars that have a mass greater than the mass of the sun, but less than 1.4 or 1.5 solar masses, whereas black holes are formed from stars that have masses greater than the mass of the sun, but less than, or greater than 3 times, sorry, the mass of the sun. Yeah, exactly what Carl said there. Good job. Neutron stars, we can say as well, a difference is that neutron stars are made of neutrons, where black holes are extremely dense, that no light can even escape. The escape velocity is greater than the speed of light. Yeah, nice. Okay, what do we say about gamma ray bursts? When in the universe do we see gamma ray bursts? So when in the universe, or where in the universe would we see gamma ray bursts? So where in the universe? When a neutron star merges with a black hole? Oh, no, actually, but that was a really good guess. If it's an active galactic nucleus, that's when we start to see the pulsars. So pulsars is what we talked about earlier. When you see an active galactic nucleus, that's when a neutron star wouldn't merge with a black hole, right? The neutron star would be completely taken in by a black hole. So that would be like an active galactic nuclei. That's your pulsar. Two merging neutron stars? Nope. Do you remember we talked about it? So we said gamma ray bursts. Remember we said our sun is very light, so we're happy days. Our sun is just going to form a red giant. And then our sun is just going to end up after red giant, it's going to form a white dwarf. Right? Kind of like low key, nothing's extremely happening. But anything greater than our sun, anything bigger than our sun is going to do a supernova. And we said if it's less than 1.4 times the mass of the sun, forms a supernova to give us a neutron star. But if it's more than 3 times the mass of the sun, because that's such a violent explosion, it does form a black hole. But as it's forming a black hole, we get a GRB, a gamma ray burst given off as well. So a gamma ray burst is given off just before a black hole forms because it's such a violent explosion, right? So what actually happens is as the star expands, then eventually everything collapses back in itself and it's in on itself and it rebounds off the core. And then because it's so violent, so much energy, that's when you get a gamma ray burst. A gamma ray burst. Okay, moving on. Okay, so we said there's 2 types of supernovas, right? We said type 2 supernovae is when that you have a star that's exploding, right? The other one we're going to learn about is a type 1a supernova. So type 1a supernova is from a binary system. Okay, so binary, if you think about binary, like binary is to do with math, like doing binary numbers, a binary system, like ones and zeros. So a binary system is when to do with 2 things. So what happens is we've got a white dwarf and it's going to accumulate the mass of an expanding red giant. Okay, so a binary system is when you have 2 stars in one solar system. So one star has already become a red giant and it's went down to form a white dwarf. And the other stars, they're going to orbit their common center of mass. The other star is when it starts to grow and forms a red giant. So it starts to expand to form a red giant. Because its layers are expanding, gravity will pull those layers in towards the white dwarf. And when gravity pulls those layers in towards the white dwarf, the mass of our white dwarf is then rapidly increasing. And eventually it's going to equal some critical mass when that white dwarf then is going to explode. And we've noticed that when we observed things in the universe, we've noticed that when all these white dwarfs reach that critical mass and explode, they all have roughly the same absolute magnitude. Remember, absolute magnitude is their brightness. And that roughly is around a number of -19, right? So that's super bright. So remember we said our sun is a G magnitude star. The absolute magnitude of our sun is around 5. So our sun's got a magnitude of around 5. Because remember, absolute magnitude 1 to 6. So we're looking here now at -19, way brighter than our sun. So because they're so bright, we can use them now as standard candles. Okay, so what a standard candle means is because they're so bright and they'll have roughly the same brightness, we can use them to figure out how far away things are in the universe. Surely there's enough energy to smoke you even in a couple milliseconds. Yeah, if you're near it, you're done. Yeah, 100%. You don't want to be near it. Yeah. So it's called a type 1a supernova. So a type 1a supernova, time 0 is how we count when we see it. And they roughly last, we can roughly observe them for Earth for around 250 days to 300 days. So type 1a supernova we use for standard candles because they're so bright and they roughly all have the exact same brightness when they reach that critical mass. We actually use them now to see how far away things are in the universe. Okay, next thing then is some of you are asking me about like the classification of stars and about how we know what our stars is. So remember we said down here, our spectral classes depends on the temperature. So O, B, a fine girl, kiss me. That's how I remember it. So O, B, a fine girl, kiss me. So remember we said our sun here is a G class star. And our sun is actually a G5 star. So there's roughly where our sun is. That's where our sun is. And that makes sense because it's in the main sequence part. So remember we said anything on this side is cooler and anything on this side is hotter. Okay. And the absolute magnitude that we observe is from 15 up to 10. But that's the wrong way around. Sorry. -15, -10. What have I done here? -5, 0, 5, 10. Sorry. It's a G5 star. There we go. Yeah. Our sun is a G5 star. Don't know why I messed that up. So our sun is a G5 star. Okay, so just to show that again, because I've got another picture. No, I didn't. So our sun is going to be a G5 star. A G5 star. Okay, so our sun is a G5 star. It's got an absolute magnitude of 5. Wait, I've still messed up. 0, 0, 5. I messed up the scale. That's the problem. Sorry. It goes from -15 up to +10. The way I've written this is the wrong way around. So sorry, I picked a bad diagram to show you what it was. So it should be -15, -10, -5, 0, 5, our sun, 10. Sorry about that. So yeah, our sun's a G5 star, and then main sequence, what our sun's going to do at the end of its life, remember we said it's going to expand to form our red giant. And when it expands to form our red giant, remember we said its outer layers are going to fly off into space, and then after it forms a red giant, that's when we get our white dwarf formed. So our white dwarf, we can see it's going to be much hotter. So our white dwarf is much hotter than our red giant, because we know that red giant, the red color, is much cooler than the white color. So it's the path of our sun. Okay, so really quickly, what do we say, even though it's terrible because I messed up the last scale? What was the absolute magnitude scale? What numbers does it go from? What numbers do we say it go to? And then whereabouts do we put the sun? You pop in the chat. And where's the sun? The sun wasn't 0. Do you remember what the sun was? What was the sun? Yeah, the sun. Yeah, sorry. So I think I've messed this up. So we're going to go back here. This is why I messed up. Sorry. I had a bit of a mare. Sorry. So sorry. This what I did was right here, and that's why I messed up, and then try to fix it again and didn't make that very clear. That's my bad. Wait, to go back. Negative 10 to positive 15 is fine. G5 is our sun. Apologies, that's my bad, right? So what we're saying over here is it's going to go from roughly here is going to be 15 up to negative 10. So there's going to be my negative 5. There's going to be my 0. There's going to be my 5. And we always place 5 around G5. So do you remember what temperature is the sun to put where the G is? And 10. So sorry, that was my bad from the last slide. 15, 10, 5, 0, minus 5, minus 10. My B. And then sun, so we said it's a G, yeah, fine, Carl. So around 6,000. So here's around 6,000, greater than 5,000. So there is going to be my, what was I saying? There's my sun, sorry. I'm doping. There's my sun. Okay, so sun, again, we always know is going to be a G5 star. Draw a line on the HR diagram to show the evolution of a star similar to the sun. So where's it going to go after the sun? So evolution of the star. After it's a main sequence, where does the sun go? So remember, it was a protostar, then it became a main sequence star, then it's going to go to, after a main sequence star, later in its lifetime, after it's fused all its hydrogen and fused its helium, it forms a red giant. Good job. So it's going to go, is it going to go straight up to red giant A? Is it going to go path B or path C? What do you think? Path A, B, or C? So when the sun, when it forms a red giant and its outer layers expand, yeah, it's going to be C, thank you, because it has to get cooler. Do you see the temperature over here is cooler? So that's why it's going to shift slightly to C. So when it goes from the sun to the giant, it's going to go slightly cooler. So that's why it's path C. Okay, so once it forms a red giant, after the red giant, where does it go next? So it's gone to path C. Where does it go next? So our sun, again, protostar, main sequence, giant, yeah, JMB, good job. Then it's going to go down into the white dwarfs, good job. So white dwarfs, we can see are much hotter, but we can see their absolute magnitude is much more positive. So it means they're much, much, much less bright, right? So even though they're hotter, they're much less bright because their magnitude is positive. Nice. Okay, label a position P, a position on the HR diagram of a star that's much redder and a greater power than the sun. So where would you put it? So it's redder and it's got a greater power. So what does the red tell you about the temperature? And what does the power tell you about its absolute magnitude? Roughly, where am I going to put position P? Path B earlier. Path B earlier. What do you mean? Left on the red and the RG. What's RGs? Path B earlier, left on the RG. Path B earlier. Oh, you meant when I did ABC. Yep, 100%. I agree. Yeah, good job. So it's much redder. So if it's redder, it's much cooler. So it has to be, if we do a dotted line up, it has to be somewhere slightly to this side because redder means cooler, right? Because we know our sun roughly is about yellow color, yellow-white. So it's much redder. So it's going to be slightly to the red of that line. And because it's much more powerful, it's much more power, it's going to be much more brighter. Remember we said the numbers from 1 to 6. 1 is the brightest. So if ours is a 5, it has to be brighter, it has to be some region higher. So basically, it could be anywhere that I've shaded in is where you could put point B. Anything that's going to be got a absolute magnitude that's got a smaller number and a temperature that's slightly cooler. So point P could basically be anywhere in that shaded region. Okay, so it says, a star much more massive than sun may become a supernova and then a black hole. Discuss whether a supernova and black hole can be placed in this diagram. So do you think we could put a supernova, could a supernova be placed at some point in this diagram? Yes or no? If yes, where? If no, why not? And could a black hole be placed in this diagram? If yes, where? If not, why not? Right and up for the sun IRM is perfect. Yeah, good job. So where do you put a supernova and where do you put a black hole on this diagram? Or if they can't go in the diagram, why do you think not? So where to put them on the diagram? So think about a supernova. Remember, a supernova we observe because of a rapid increase in brightness. Think about the temperature of a supernova. Look at the temperature on our scale. Yeah, thank you, Ahir. Good job. So black holes are going to be really cold, right? So black holes are going to be really cold. So they're going to be somewhere way over here. And think about their absolute magnitude. Can we, so remember, absolute magnitude 1 to 6 is what we can observe from Earth. Can we observe black holes from Earth? What do you think about their numbers? Number 1 is the brightest, 6 is the dimmest from the Hipparcos scale. So if they're really cold, there'd be somewhere towards the right. And what about their absolute magnitude? What numbers do you think it would be? Yeah, we can't observe them from Earth, right? Good job. So that means their absolute magnitude must be a number much greater than 6, much greater than 6. So there's number 15, there's number 6. So it must be much greater than 15. So I would say a black hole, yeah, Ikir, a black hole can't go on the scale because it's much colder than 2,500 degrees Celsius, which is on our scale, or much colder than Obeah or Kiss-Me, much colder than an M-class star. And also it's going to be much dimmer. So it's much dimmer than the positive 15 magnitude there. That's why we can't see it. Okay, so what about a supernova? Where would we place a supernova, or can it go on this diagram? Where would we place a supernova, or can it go on this diagram? So where to place a supernova, and can it go on the diagram? So hopefully you're thinking supernova is a rapid increase in brightness. Yeah, thank you. It's going to be much brighter, much hotter. It's probably going to be much brighter than a -10 and much hotter than 50,000 degrees Celsius. So it'll be somewhere way up here, but it's probably not going to be on it. So supernova, we're going to say, has a higher temperature than 50,000 degrees Celsius, or Obeah or Kiss-Me, a higher temperature than an O-class star. And it's going to be much brighter than -10. Much brighter than -10. Yeah, perfect. Okay, I think just for the sake of time, the last thing I wanted to talk to you about was probably Hubble's law. I think this is quite cool. So cosmic microwave background radiation, if you look at it, this is called the CMB. You might have heard of it. CMB is the cosmic microwave background radiation. It's the radiation left over from the black hole. It's the radiation left over from the Big Bang, and is one of the reasons how we know, or one of the reasons why it's most evidence the Big Bang had to happen, right? Because we can see the universe has got radiation left over, and if we look at the temperature of it, it's 2.7 Kelvin. So it's the temperature of space, basically, the temperature of that background radiation. So Hubble's law, you've probably heard about. Hubble's law was, what he did was he observed that when we look at space, let's say we're on Earth here, and we look at the stars around us, all the stars around us are moving away from us. So they're all moving away from us. So he said all the stars, the light is redshifted. And he saw that V, the speed that they're moving away from, is directly proportional to their distance. So this star that's further away from us, it's moving at a much faster speed away from us than the star that's close to us. So again, what he saw was stars that are further away are moving faster because they're further away from us. So he said the speed is directly proportional to their distance. So he has speed is equal to some constant times the distance. So he said the speed is equal to, he called it the Hubble's constant times the distance. So we can use that now to calculate what the age of the universe was. Okay, because we know speed is equal to distance divided by time. So here I've got V equals h times d. So time is going to be distance divided by speed. So here, if I take distance divided by speed, I get 1 over h. So 1 over h is going to equal to the time. So can you figure out what the age, what the time of the universe is, if that's the number we're using for h? And a parsec, remember we said earlier, a parsec is our reference of distance. And on your data sheet, I'll just write it here for you so you don't have to bother looking at your data sheet. A parsec on your data sheet is, oh, I've lost it. Parsec on your data sheet is 3.08 times 10 to the power 16 meters. So a megaparsec, mega is times 10 to the power 6. A megaparsec is 3.08 times 10 to the power of 22 meters, because it's a million, so 6 times bigger. Apparently some RF static comes from it. RF, radio frequency. Is that what you're talking about? Radio frequency. Ah, yeah, so you're talking about how they Yeah. So the first guys who were looking at the universe, what they did was they had big radio telescopes, and they found there was always like a constant noise. And they actually thought the constant noise was because birds had pooed all over their radio telescope. Yeah, so they had to go clean it. And then when they cleaned it, they still found out there was all this constant noise. And then there was another group of scientists in another part of the world who also found the same group of noise. So they figured out that noise they're detecting was the radiation left over from the Big Bang, or the theorized Big Bang. 5.1 times 10 to the power negative 28 in seconds. That's not I got in seconds. I got something much bigger. Remember, it's 1 over Hubble's constant is the time. So Hubble's constant is 65 kilometers per second. So 65 kilometers per second is 65 times 10 to the power of 3 meters per second per megaparsec. So what you do is 65 times 10 to the power of 3, divide it by 3.08 times 10 to the power of 22. That's what Hubble's constant is. We got to do 1 over Hubble's constant to get the time, and that'll be your time in seconds. So you got to do 1 over that number. So you do 1 over 65 times 10 to the power of 3. And you divide that by megaparsec, because it's kilometers per second per megaparsec. You get 1 over it, and that'll be your answer in time in seconds. So once you get in seconds, remember, you divide by 60 to put it into minutes, divide by 60 to put it into hours, divide by 24 to put it into days, and divide by 365 to put it into years. So tell me, how old in years is our universe based on Hubble's laws observation? So Hubble's constant h is 65 kilometers per second. So it's 65 times 10 to the power of 3 meters per second. And it's per megaparsec. So that's why you divide by a megaparsec. Divide by 3.08 times 10 to the power of 22. And that's your value for Hubble constant in seconds to the minus 1. To find what is in seconds, then you have to do 1 over your answer. Four. Yes, lovely. J and B, that's the answer in seconds. Yeah, nice. So again, you're doing 65 times 10 to the power of 3, divided by 3.08 times 10 to the power of 22. You do 1 divided by the answer to give you your time in seconds. So that's how J and B got 4 times 10 to the power of 17. So that's how I got in seconds. So J and B, just convert that into years. Yes, Ig here, good job. So 1.5 times 10 to the power of 10 years is what you should get. So Ig here, I'm just going to put up here, got 1.5 times 10 to the power of 10 years. So what that is 15 times 10 to the power 9. So that's 15 billion years. And if you Google the age of our universe, it comes out roughly around something between 12 to 14 billion years old. Okay, so clearly you can see that's an overestimate. Does anyone know why it's not exactly the age of the universe? What's wrong with what Hubble observed? Yeah, J and B. Yeah, brilliant. So I know we're a little bit over time, but I find it quite interesting. Why do you think the age of the universe is a little bit over? So we just said that what Hubble noticed was, and it works really well for stars that are close to us. For stars that are close to us, we do see that ones that are further away are moving faster. But he said it's proportional to distance. He said that it's a constant speed. So he thought our universe was expanding at a constant rate. But does anyone know what we now think? And that's why it's a different number. So he thought our universe was expanding at a constant rate. So that's why he said the speed was directly proportional to distance. Things that are further away are moving faster, but it's expanding at a constant rate. Does anyone know what we now think the universe is? Yeah, here. So the universe is accelerating. So what we did was we observed really distant supernova, and they're much brighter. Pardon me, they're much dimmer than we thought they were. So because they're much dimmer than they should be, that must mean they're further away than what we expect them to be. So the only way they could have been further away than what we expect them to be must be because the universe now is accelerating. So it's mad because it's a topic, especially that we know so little about right now. So like the first image of a black hole by a woman actually was so recent. It wasn't even that long ago. It was like, I think it was in the last year. So it's mad how much research is just currently happening in this topic. So it's quite exciting. Okay, so that's a bit of a whirlwind introduction to astrophysics. But the other slides are there if you want to have a look at them, because if you just think they're really interesting. So TRAPPIST-1 is what we did was when I was at school, people thought exoplanets were like really rare. So exoplanets are planets orbiting different solar systems. But now they find loads of exoplanets around loads of different stars. And this one's really cool. It's called TRAPPIST-1. So this is all the exoplanets around TRAPPIST-1, and there's the same number of exoplanets that there are around the of orbit of the number in our solar system, and they find ones where they have so perfect distance away from the sun that they think they could have liquid water on it. It's called the Goldilocks zone. What books I recommend for astrophysics? Honestly, hopefully you do our lessons, but physics and math tutor is pretty good from it. Is there planets with two suns? Yeah, so two suns is a binary system. So there are binary systems in the universe. Okay, so if you enjoyed the lesson or enjoyed our 4 weeks together, which hopefully you did, please go and give us a review on Trustpilot, because we all know everyone goes to Trustpilot. Static Spark, you've been to TRAPPIST-1. What? We all know that everyone goes to Trustpilot to see like where you should eat, where you should go. And we're trying to show that a lot of kids, right, they don't have a physics teacher anymore, or they don't have the resources and skill they need, but they don't know about it yet. So, and everyone reads Trustpilot. It's really nice if you enjoyed it to give it a review. And then hopefully you're going to join us for the year, right? So we kind of had like a whirlwind of 4 weeks of me trying to show you different topics that you're going to do in year 13 to help you feel a little bit better when you go into class, because you already have some background knowledge. But hopefully you know already about our full course. Our full course will start in September and it'll go the whole way to May. There's going to be a total of 108 hours of lessons. There'll be lessons like this. There'll be homeworks. There'll be homework video solutions. You'll also have mods in the lessons like Garrick, but to help you out with questions that maybe I haven't got to yet. There'll also be like a group chat as well, kind of thing, but it's not really called a group chat. It's just like a way that we can interact with each other, and you can post homeworks. And we do all of it again because that basically Carl Sagan, yeah, I like his stuff. Tutors in London are mad expensive, so you probably all know people are tutors and thinking about it, and they cost like £60 an hour, right? I charge 50, but I don't do it anymore, and that's why we created My Space, and that's why I want to work for here, because when I was your guys' age, no way could I ask my parents for £50 a week, right? I was lucky if I got a £5 or a pound a week in pocket money. But if you look at it, it's coming out like 4,800 for the full year just to have a physics tutor. Okay. Whereas for My Space, we're trying to outreach that to more kids. We're trying to show you there's more options for you guys. So if you look at the YouTube link, there's a link there about WhatsApp. Just make sure you go on it because it's limited spaces. And we're going to give it to you for roughly £400 to £600 depending on the course. Right. So that works out basically £5 a lesson, which is so much more different than paying £50 a week or £50 a lesson or £60 a lesson even for some physics tutors. Ashna, you're so welcome. And there's a 14-day full refund guarantee. So if you don't like it, you always get your money back, right? But hopefully you love it. And there's also the ultimate pass. So a lot of you are doing like free subjects for A level. And this is a even bigger discount. So it comes like £2 or £4 a lesson now. So you just know there's Dario and Neil who's doing math. Dario's also doing some physics for the younger years. There's me. There's English with Louis. There's LaJoy, he's doing chemistry. And so is Dav, so he's also doing chemistry. Yeah, Nally, the times. So I got them for you because we talked about it last time. So there's the times of the lessons that are option T. So me, I'm doing Tuesdays from 5:40 and Fridays from 6:50. And then the other ones there are just to show you where they all kind of fit into a timetable. So again, my course, if you just do that link, is around 400 to 600, depending on the course. But remember to use a WhatsApp because you don't want to miss that discount in the WhatsApp, right? Because it's like a 40% discount. It's mad. Just because you guys have been interacting with the summer school. So hopefully I see you guys in the September course, because it'd be nice just to kind of keep the same people, and I kind of know you a bit now. And then we just kind of go through the whole of the year 13, and then we spend a lot of time revising year 12 stuff. I ate the hadrons. What are you talking about? But yeah, if you also need like advice or anything or talking about careers, obviously I'll also be there as well in the September course to help you out with that. But you guys are free to go. I hope you have a lovely rest of your summer. Probably have like a week left. Carl, see you in September. Happy days. And hopefully if you don't join in September, at least I've helped you out enough to help you feel a little bit better about going into year 13. Nadia, see you in September. Happy days. Iran, you're so welcome. Carl, Garrick, no. Yeah, Garrick's got school himself, doesn't he? He's going to have uni. Bye, Priscilla. You're so welcome. Bye, Jen and B. You're so welcome. I hear you ran all the way there. What are you talking about? Running to SAG A is crazy. Are you just trying to? Are you still trying to get in there that you don't names of different stars? Oh dear. I need to get some food. I feel my energy's dropping. Right. I hope you have a lovely day. And thanks again for summer school. It's been great. It's been a pleasure teaching you guys. Hopefully I see you in September.